In the last 3 lectures, we have learned first law of thermodynamics and the second law of thermodynamics. Okay, first law of thermodynamics. What's the first law of thermodynamics?
So all the energy in the universe is conserved.
Yeah, so energy of universe is constant, yeah. The form of the energy can change from heat to work, for example, but however, the energy of universe is constant. That's the first law of thermodynamics. Not energy of system, energy of surrounding. It's total energy in the universe. It's constant. Okay, then how about second law of thermodynamics? Very back. What's the second law of the thermodynamics? Entropy in the spontaneous reaction, it always increases. 80%. The other 20% is missing. What is missing? Entropy of universe is increasing by the spontaneous process. Okay? At equilibrium state, entropy universe is constant. However, whenever you have the spontaneous reaction, any kind of the forward reaction or any kind of natural process, it involves the increasement of the entropy of universe. Okay? These two laws is, very general law, but unfortunately, as I mentioned, it talk about the universe. It's not talking about only the system. So that's why it's very difficult to really apply it to understand whether my system itself is already in equilibrium state or not, or whether my system is going to the forward or backward. We cannot really tell from this first law and second law of thermodynamics. Okay? So that's why we're actually heading to derive the Gibbs energy function. And if we are lucky, we're going to see the Gibbs energy function today, and which you already know. Okay, so before we go to the actually Gibbs energy function, let's actually now learn the third law of the thermodynamics. Okay? So this is probably number 4. It's related to the entropy. So entropy, we said that entropy is irreversibility, degree of the irreversibility. Yeah? And also entropy in the physics, typically, in the physics, or in the solid state physics especially, or in the quantum mechanics, when they actually talk about entropy is defined as the randomness of the system. So entropy of system is representing the randomness of the system. So if you look at actually the statistical thermodynamics, and which we're not going to learn in this class, but I heard that you learn actually little bit of statistical thermodynamics in the physical chemistry too. And you see that, okay, there's the electron, and then there's the different actually the orbital. And then when the actually energy is coming, it's going up and then emitting and then coming back. And then the chance to actually fill up all this electron, and that actually give the entropy kind of the expression. And then when you have that like a ds equal to minus ln k total or whatever, yeah. And that's actually statistical approach. But whatever, those statistical approach really tell that, okay, the entropy is directly related to the randomness of the system. Entropy of system, entropy itself is degree of the randomness, basically. It's dictating the randomness. So all the natural process, of course, we want to make it more randomized. We want to actually make everything disordered. Yeah? So it's become more random. Okay? We don't like a very ordered state. So for example, like this is actually the question number 1 for your final exam. Explain third law of the thermodynamics to your grandmother, to my grandmother. Okay? And one of the best answer, you are lucky, one of the best answer is, so during the weekend, if you actually fix if you clean up everything of your room, you put everything in order, you clean up everything, but by the natural process during the week, it becomes disordered. That's the third law of thermodynamics, basically. Well, that's second law of thermodynamics. That's the second law of thermodynamics. By any kind of natural process, it always make system become more disordered. Okay? So entropy is degree of the disorderedness. Okay? And now, if you think about entropy as directly related to disorderedness, if we actually bring our material down to the 0 degree Kelvin, what will happen? So for example, I have air. Let's just I have just pure nitrogen. Okay? We know that from the ideal gas law, when you actually bring this 1 mole of gas from room temperature to the 0 degree Kelvin, the volume become 0. Theoretically, it's impossible. No, practically it's impossible, but that's actually theory of the ideal gas law. Yeah? So volume is expanding with the temperature, but if you go down to the 0 degree Kelvin, the volume of gas becomes 0. That's the ideal gas law. Okay, so like this. So when you have for example, pure iron, okay, FCC structure, okay, if you assume that there's no defect at all, so all the lattice of the FCC site is occupied by the iron atoms, okay. So typically when you increase temperature, there's more vibration of the atoms from its original lattice site here. So you have more and more vibration, okay? And so it's very difficult to say that where's exactly my iron, yeah? It's vibrating, yeah? In every position it's almost same, but it continuously changing its position with the time, okay? But if I take this iron metal, FCC, and if I decrease temperature and lower, then the vibration becomes smaller and smaller. Yeah, because it doesn't have the energy, it doesn't have temperature, so it will probably slow down its vibration, or even the distance when it actually moves can become smaller and smaller and smaller and smaller. And if you become 0 degree Kelvin, by conceptually we can think about that. Okay, all the atom will just stay exactly one position. Exactly that lattice position of the FCC. There's no vibration. When you're vibrating, it means there's some energy. So at 0 degree Kelvin, probably all this atom, of course between the atom there's some repulsive force or some attraction force. However, if all those things is cleaned up, and then if we make actually the atom, if we bring this material to 0 degree Kelvin, there's no movement of the atom at least. So it stays exactly same position. So this actually the thing is very ordered state. Yeah. So for example, if I have FCC material and iron, I know exactly where's my lattice point, and if I click the lattice point, I can directly hit my iron atoms. There's no disorderedness. I know exactly where's my iron atom in the lattice. Okay? So in thermodynamics, this means there's no disorderedness. Okay? We know exactly every point. We know exactly all the position of the atom. So there's no disorderedness. So let's think about same thing. Okay, iron, pure iron, FCC. How about pure iron, BCC? It's a different structure, but however, it's the same theory can be applied. Yeah. How about pure, for example, FeO, iron and oxygen? If you know the lattice, there's this, FeO is kind of NaCl structure. So you have the, it's kind of FCC structure, but one side is occupied by the iron, one side is occupied by oxygen. Yeah. And if it's in the high temperature, there will be vibration of the iron atom, oxygen atom. If I decrease temperature to the 0 degree Kelvin, if I know there's the iron, the next one should be oxygen. And iron, oxygen, iron, oxygen, iron, oxygen. I know exactly where's the position. Okay? So third law of thermodynamics is conceptually derived in this way. So third law of thermodynamics is basically, okay, if I have crystalline phase, stoichiometric crystalline phase. So this is important, stoichiometric phase. Stoichiometry means you have certain number of the, for example, A atom and B atom have making certain structure. Okay? So if I have those kinds of the crystalline phase, the disorderliness at 0 degree Kelvin should be 0. That's the third law of thermodynamics. So third law of thermodynamics is basically entropy of at 0 Kelvin equal to 0. Because entropy is directly related to the disorderliness. But what is 0 is very important. Entropy of the solid crystalline, so crystalline, stoichiometric material for crystalline means it's a solid, okay, stoichiometric. So this is all similar actually word. Stoichiometric solid phase, we call it compound. Okay, that's actually kind of the terminology we are using in the solid. So compound or stoichiometric compound, stoichiometric solid phase, which have certain crystal structure. That entropy at 0 degree Kelvin is 0. Okay? Then let's think about this way. Okay, liquid ion at 0 degree Kelvin. We can supercool the liquid ion, and when it becomes 0 degree Kelvin, is it going to be 0? Entropy should be 0? No, it is not. So, because it's not crystalline phase. Okay? In the liquid state, there is actually the distance between the atom. We don't know exactly what's the distance. Okay? It's not really crystalline phase, so we don't know exactly where's the atom. So even you cool it down, you don't have a crystal structure. So that means we cannot really dictate where's exactly my atom. So that's why the entropy at 0 degree Kelvin cannot be 0 for the liquid phase. Okay? Gas phase is same thing. We don't know where's the position of each molecule or atoms. Okay? But when you have the fixed crystal, when you have the solid phase with the fixed crystal structure, then we can more or less know all this position at 0 degree Kelvin, because there's no disorderliness, there's no vibration of atom. So for example, so if I have pure iron, FCC, pure iron, BCC, okay, and the carbon, solid, graphite, for example, carbon, diamond, it's all possible. All this one is 0. But if you go to the now, for example, iron, nickel, FCC solution, it's a solid state, so we call it solid solution. So it means, for example, let's assume I have 50% of iron, 50% of nickel, solid solution. It's FCC structure. However, when you mix it, let's assume I have the iron here. The chance to have the nickel next to each other is not, the chance to have the nickel next to each other is the 50%. Yeah? So we don't know exactly whether this position is really occupied by nickel or iron. So there's randomness here. And then there's on top of that, there's the vibration, of course. But when you take this one at 0 degree Kelvin, you don't know exactly whether this position is iron, this position is nickel, because it can be randomly distributed. Yeah? So that's why solid solution is not 0. Entropy of solid solution at 0 degree Kelvin is not 0. Although pure iron, pure nickel is 0, however, solid solution is not 0, because we don't know each position exactly in the solid solution. So this is different from the stoichiometric compound. So for example, now, let's take this one. Fe3 carbon. It's kind of cementite. Fe3C cementite. And this have certain crystal structure. And then within the crystal structure, there's a position for the ion, there's a position for the carbon. So at 0 degree Kelvin, the entropy of this one becomes 0. Okay? And this is stoichiometry, 3-to-1 ratio. Certain ratio of the atoms to make that crystal structure. Okay? And this one, iron nickel, I can change from 0 to 100. Whatever composition, yeah? So it's not stoichiometry. There's no certain fixed number of the ratio of the ion or atoms to different elements to define the crystal structure, yeah? So that's why we call it solution. Okay? So the compound, the opposite side of compound is basically solution. Okay? So solution is not 0, but compound is 0. Okay? Same thing, H2O ice, solid, become 0. Okay? But as I mentioned, all this liquid phase, ion, liquid, or oxygen gas, this is not 0, yeah? And this is not 0. Okay? So this is definition of third law of thermodynamics. Okay? Good? Third law of thermodynamics. And third law of thermodynamics is very important to calculate entropy, actual entropy now. So then if I apply the third law of thermodynamics, S ds, do you recall this one? Okay. And so now if you actually derive this one, delta S will be, this integral of A to B actually applied. But now because of third law of thing, so S 0 Kelvin is 0. So this will be from 0 to certain temperature. This will be integral 0 to certain temperature Cp over the T dt plus del S at 0 degree Kelvin, and this is 0. So we can exactly quantify what's the entropy at the absolute at the given temperature. So we know the absolute value of the entropy, for example. S, for example, this means S at the certain temperature in Kelvin equal to integral of Cp over the T from 0 degree Kelvin to the certain temperature, dt. Is this okay? And because S at 0 degree Kelvin is 0. You good? That's why third law of thermodynamics is very important to calculate absolute value of the entropy. Okay? Compared to this one, we have to really talk about this. Okay, entropy have absolute value because of the third law of thermodynamics. How about enthalpy? Enthalpy. Enthalpy at 0 degree Kelvin for the pure ion. Is it going to be 0 or not 0? Enthalpy at 0 degree Kelvin is not 0. Because the enthalpy, so you learned actually the energy well like this. For example, I believe you have learned like kind of this is energy. And when you have ion, pure ion, when you have a certain distance, and you have this kind of potential well, I think you have learned this one, and this is basically distance of R here. So at 0 degree Kelvin, the position for the distance between this one is this one, okay? And then with the increasing of temperature, it actually have some sort of harmonic actually the behavior, so it's pushing in this direction, yeah. So you learn this kind of the atomic potential, and then at atomic potential at 0 degree Kelvin at this position is equilibrium actually distance between the atoms to minimize the energy, yeah. So, there's energy. It's not 0, yeah. There's energy. So when you have A and the B together, If you want to take this one off, you need certain energy. You have to tearing the you have to break actually this bond, iron and iron bond. You need energy to break them. So there's the energy. And this is enthalpy. This is enthalpy. Okay? So all the AB initial calculation, so for example, this the first principle calculation or AB initial calculation by using the quantum mechanics, they are calculating actually enthalpy at 0 degree Kelvin, more or less. Okay? So that's the enthalpy. So enthalpy, unfortunately, we don't know what's the energy. So for example, now, luckily now we have the quantum mechanics, so we can calculate something. There's still actually certain amount of the approximation doing those kind of calculation, but we more or less calculate enthalpy value at 0 degree Kelvin for the atoms. Okay, pure iron FCC, pure iron BCC, and etc. But in the 19th century or 18th century, when the thermodynamics was first developed, there was no such kind of the knowledge. Okay, so people cannot measure the enthalpy at 0 degree Kelvin. So they have to make a certain assumption. Okay, that assumption is when, instead of actually using this absolute value, we are using certain relative value for the enthalpy. We're going back to actually this point later. So, but what I want to actually really stress it out here is, because of third law of thermodynamics, entropy have absolute value. However, enthalpy doesn't have the absolute value. Enthalpy is relative value all the time in the thermodynamics. Okay? So, strictly speaking, Gibbs energy is not absolute value. Gibbs energy for the material is not absolute value. It's kind of relative value based on certain assumptions, certain reference state. Okay? So we're going back to actually that one. Good? Third law of thermodynamics. Okay, now let's move on to the another topic, which I don't like that much. But all the thermodynamic books still have this, the so-called heat engine problem. So there's example always showing the heat engine. But I don't think this is really necessary for the material engineering, because we don't care about heat engine. Heat engine is really for the, mostly for the actually the mechanical engineering. That's for the engine design, originally. And so we don't care that much, but because it's so well known, actually, the example in the thermodynamics to explain actually the efficiency of the heat engine. So, and also Carnot engine and all these kinds of things. Very, very popular actual concept. So that's why we're going to look at it. So heat engine. Okay, let's take this kind of idea. Let's assume I have here, this is exactly the same diagram I have in my lecture note. So let's assume this is heat reservoir. And then this is another heat reservoir. Okay, and then let's take this one is engine. Okay, and of course, so this temperature T1 or T2, let's take it, how I define T2, and this is T1, and T2 temperature should be higher than T1 temperature, of course. So heat is coming from the heat reservoir number 2, and then given to the heat engine. So let's take this one as a Q2. So delta Q2, I'm injecting delta Q2 amount of the heat into the engine, and engine will do the work, of course. Then engine will do the work, okay? And then when engine is finishing the work, and it actually also have the heat loss to the surrounding. So there's another one, delta Q1 surrounding. So this is heat loss basically. So theoretically, if I actually have the heat reservoir surrounding, give the delta Q2 amount of the heat, and if all this heat is used for the work, then we can do the maximum amount of work. Okay? But unfortunately, there's always heat loss. That's why we cannot do the maximum amount of work. Okay? So the definition of the heat engine, efficiency of engine is easily defined in this way. The amount of work which is done by, so delta W, the amount of work done by the engine divided by the amount of heat I enter. So that's the actual definition of the efficiency of the engine. Okay, I mean this is very easy to actually understand. So if these two is same, efficiency is 1 or 100%. Yeah, is that okay? And one of the most famous actually the heat engine people actually conceptually design is so-called the Carnot engine, which is proposed by the scientist called Carnot. Okay, so let's look at this one. Or they call it cycle. Carnot cycle for the heat engine movement. Okay. So it's kind of piston. Okay. So we have, I think when you actually, I don't know what's the course name now. When you actually learn the engine, so like a 2-cycle engine, 4-cycle engine in the high school, you learn actually how does the engine is typically actually the typically working. So we typically inject inject the fuel and the gas and then ignite. Then it actually have gas expansion because the fuel is actually start to actually the combusting with actually, I mean combustion, have the combustion and it generates gas phase, yeah. And so you have expansion of your system and that actually make work, okay? And then once that work is finished, it actually it's shrinking back again because the temperature of the gas is decreasing, so the volume is decreasing, and then you're actually also releasing the valve, so its gas is going out. So it's shrinking back. So it's expanding and then compression, expansion and compression. This is kind of engine cycle, okay? And one of the engine cycle actually proposed by the Carnot is actually the combination of the 2 expansion system and 2 compression system, okay? So he explained in this way. Okay, let's take initial state here. Okay, I have certain temperature and at the certain temperature I have the P and the V, and then he have 2 expansion system. So this is isothermal expansion. So expanding, my volume is expanding, isothermal expansion. And then he said that, okay, if I do it's kind of all this one is reversible amount of work, because I mean, if you have any kind of irreversible work, you are losing heat, yeah? Because of irreversibility, the part of work become heat, yeah? So we are losing efficiency, yeah? So Carnot actually proposed, okay, let's take everything is reversible process possible to maximize my efficiency, okay? And then he proposed, okay, so in the first cycle, we have isothermal expansion. So ISO-T, isothermal expansion. And then he have adiabatic expansion, delta Q equal to 0. So adiabatic process, it means there's no heat exchange between the system and the surrounding. Okay? And then there's another one, compression now. So this is isothermal compression. So it's a reverse one. And then isothermal the adiabatic compression, like this. So, according to the heat engine here, so if you actually assume this is our heat engine, and then we have, in the beginning, we have a heat reservoir which have T2 temperature. So we are taking T2 temperature into the heat. So this is temperature T2, and then this is temperature T1, because we are losing actually the heat to the heat reservoir 1, T2 and T1. And then let's take this one. This process is process number 1, 2, 3, 4, like this. So this is 2, And this is 4 equal to 0. Okay. So first of all, let's look at the total amount of work. Delta W total by this cycle of the engine. The amount of work we are doing is basically this side here, inside of this area here. That's the amount of work we are doing. Okay? Because when you do the work here, you are doing this amount of work, and when you compress it, this amount of work is going back. So this area is basically total amount of work, yeah? And so this one is delta W1 plus delta W2 plus delta W3 plus delta W4. And that's the total amount of work. And then now delta U of system. So the change of the internal energy of this heat engine, delta U of system, should be delta Q minus delta W, yeah? Okay? So delta Q minus delta W. So in terms of delta Q, because we have two adiabatic process, so delta Q1 plus delta Q2, delta Q3, and delta Q4, but delta Q2 and Q4 is 0 basically, yeah? So this will be but this is 0. And then total, yeah? It should be total. So this is total delta Q for one cycle and total delta W for one cycle. And this become 0 because internal energy U is state function. So we start from here and we come back exactly the same position. Okay? So delta U should be 0. Is it good? So if you look at this one, delta Q1, delta Q3, which is happening during this isothermal expansion, equal to same as total. Is it good? Now, so this was the system, internal energy, and now let's look at actually the entropy point of view. Okay? Entropy of system. Okay? So, now delta S of system, so it's one cycle again, delta S of system is delta S1, delta S2, delta S3, delta S4, yeah? Delta S is defined by delta Q of the T. Okay? In the first cycle, so T2 temperature, and then Q1, yeah? So delta Q1 of T2 temperature plus 0, because delta. So for this process, the Q equal to 0, so it's 0 here, and then T1 plus 0 equal to 0, because entropy is also state function. So you move from here and coming back. Internal energy become 0. Change of internal energy become 0. So you came back to the exactly same position. And delta S should be 0 because it come back to the exactly same position. Okay? So, it's good. Then, from this one, we can derive that. Okay, delta Q1 of the T2 equal to minus delta Q3 of the T1. Okay? So now we want to actually equate this one and this one together into here. Okay? So this delta, the efficiency of engine, delta W, this delta W is actually total amount of work, yeah? Total amount of work done by the engine divided by delta Q2, which is I gave actually from the surrounding. Okay? So then, let's take this one. This will be, so let's take this one as epsilon. So epsilon is the efficiency of engine. So epsilon equal to delta W total divided by delta Q2. And delta W total is same as Q1 plus Q3. Yeah. Over delta Q2. Q2. Just a second. We have to be very careful here because we actually combining two different actual notation here, yeah? Okay, let's take this way. So we are not confusing here. So 1, 1, 1. So let's take this way. Q1, Q2, Q3, Q4. So each process, and Q1, Q3. Is okay? And then this one, S1, S2, S3, S4 process here is Q1, Q3. And then Q1, Q3. And then this will be Q1, Q3. Very, very confusing. I'm sorry about it. Okay, so now let's look at this one again. This is not very actually the good way actually I did it. Theoretically, okay, yeah. So here, I'm very sorry about it. So Q1 and Q3 here. So let's look at here again. So this one is the delta Q3, Q1, and this is delta Q3 here. So let's take this way. Very sorry. So this is delta Q1 we define, delta Q3 we define. And however, this delta Q1 is actually same as this delta Q2 I gave for the work. And then this is basically heat loss, and this is heat gain, yeah? So this is delta Q2, and this is same as delta Q1. I'm very sorry about it. So then, if I actually put it back here, and this will be Q2 Is it okay? Yep.
You told that delta Q2 equals 0 and the bottom side of the right.
Here, yeah.
How is it possible that delta Q1 is equal to delta Q2 in the middle of the whiteboard?
Delta Q1. So yeah. So this is actually my actually apology. So I try to actually explain. Okay, the amount of heat is coming in is delta Q2. Okay, here in this actually the schematic diagram, the heat coming in during the work is delta Q2. The heat actually losing during the end of the work is delta Q1. Okay, but this is cycle number 1, cycle number 2, cycle number 3, cycle number 4, and if you actually sum 4 cycle, it becomes 1 actually the closed cycle. And during the cycle number 1, the amount of heat I'm gaining from the surrounding is delta Q1. Is it okay? Because I have to gain so basically if I want to expand my system, I have to gain the heat from the surrounding, yeah? So this notation here is same as this notation. So in the first cycle, when actually expanding, isothermal expanding, let's assume I have the heat I actually taking from the surrounding is delta Q1, and that should be, in this schematic diagram, this should be same as this delta Q2. Is it okay? Because this is my system. I am doing actually expansion. So I have to take the heat from the surrounding. Okay? And during that expansion, I'm gaining this plus this amount of heat from the surrounding. Okay? However, if you look at it, this is 0. So this heat related to the cycle number 1 should be same amount as the heat I'm gaining from the surrounding in this schematic diagram. I try to connect this one and this one because I used actually the wrong notation here. Or I can scratch everything. I can start from the beginning, but let's just take it in this way. Is it okay?
So if it is, the second process is not a diabatic process at all.
Then this plus this should be this one. But we just make a very ideal case. Okay? So let's just take a very ideal reversible process and proposed by the Carnot. And I mean, this is his design. Okay? If you just take actually his design, and his design is combination of the isothermal expansion and adiabatic expansion, and then isothermal compression and adiabatic compression. So that's the basic idea of him. Okay? Because all this actual process can be reversible process. And then we assume that everything is reversible process, of course. Yeah? Is it okay? So there's no heat, there's no degeneration of the work to the heat. Okay? So all work is work and all heat is heat. Is it okay? You good? So this notation here, this one without actual circle is different. This one is related to this one, and this one related to this one. Okay? The notation inside of circle 1, circle 2, circle 3, and circle 4, just showing the actually 4 different cycles for the one loop.
And
yeah?
what I'm confused is, well, for the lack of the appropriate expression, but what we've done to the engine, what we've given the heat is delta Q1, no?
No, we are giving the delta Q2 according to this schematic diagram.
But
In this one, yeah, delta Q1,
so
circle 1.
When calculating the efficiency of engine, if we change delta Q2 to
Equal to delta Q1. Yeah, or the other way around. Same, because I just defined this one as this way. That's why it's like this. But you can also define this one. Same. Yeah. Is it okay? Sorry about it. Because this two is completely different notation, okay? Is it okay? So, inside of this cycle is the Q1 circle, Q2 circle, and etc. In this schematic diagram, just Q2 and Q1 without the circle. So that's why it's a little bit confusing. I'm very sorry about it. I should actually make it. I should do it properly from the beginning, but it's too late. That's why let's just keep it like this. And you can change the notation internally by yourself, okay? And then if you're doing this way, or if you're doing, if you're using this reference, or if you're using this reference, whatever you like, because it's the same value actually. Okay? So if you do this way, then I can just change this one to this 2 notation back again. Then this will be basically 1 plus delta Q1 over delta Q2, yeah? Okay? And then if you look at this one, it's very bad. And this is same as delta Q2 and delta Q1, yeah? Okay? So if I actually move this one to here, and then move this one to the other side, so T1 over the T2 will be here delta Q1 over delta Q2 minus. Is it okay? So I want to just derive this actual relationship here. And so delta Q1 over delta Q2, delta Q1 over delta Q2. So this basically become 1 minus T1 over the T2. Is this okay? So this is the theoretical efficiency of engine. E epsilon, the engine efficiency, is 1 minus T1 over the T2. And we already assumed that inside this end, we already assumed that everything is reversible process. There's no irreversible amount of work. So that means we are not losing any amount we are doing maximum amount of work. That's we already assume. However, because of the heat loss to the surrounding, it's because during the one cycle, you have to go back to the exactly same position. The engine should go to the exactly same position. You cannot move engine in this way. Yeah? You have to go to the engine expanding and then compressing again. So because of that actually condition, we have to get a certain heat from the surrounding, and then we have to lose a certain heat of the surrounding to get the compression process, okay? And so because of those kinds of actual constraint, and the heat efficiency, the engine efficiency, epsilon equal to 1 minus T1 over the T2. Okay? So if you look at this actually this one, so as I mentioned, we already maximized the work because we assume this is reversible process. And however, because of the temperature difference between the input and output, we are losing efficiency. It cannot be 1. So if you have the T1, T2 equal to same, engine doesn't do work at all. Yeah? Engine don't do the work at all. So basically engine is moving like this. There's no work. Yeah? Because it's just going there, no compression, out, going there and no further expansion, then coming back. Okay? So 0 amount of work if the temperature is same. So in order to really maximize the engine efficiency according to this kind of the schematic, actually the engine is this kind of idealized engine. Either T1 become 0 degree Kelvin, T1 0 degree Kelvin, or T2 should be infinitely high. So unlimited, as high as possible, T2 temperature. Then you can get the engine efficiency become almost 1. Okay? But both of them is very difficult to realize there in reality. Okay? So, there's still a lot of people actually talking about, okay, I have engine efficiency almost 100%. It's a very, very, very difficult actually. It's very, very difficult. It's almost impossible. Theoretically, it's impossible because there's no reversible work. There's always certain irreversibility in the work. So you are losing certain amount of the work to the system, okay, because of degeneration of the work. So it's impossible to have 100% engine efficiency. Yeah? No? Okay. Is it good? But as I mentioned, this is, I don't know why we are learning this one. I want to really say, if I can change the textbook, I want to completely delete this one. It's almost no news at all in the material engineering. But now at least when you actually talk with your friend in the mechanical engineering, you can say, okay, I know a little bit about Carnot engine. And okay, I know engine efficiency a little bit, That's the only reason, actually, we are still probably digging a little bit of this one. And it's classically, people actually using this example for the entropy. So that's why we actually still using this one. Is it okay? There's nothing else. Okay. And for example, you're not going to see this one at all in your midterm or final. Even not your homework. I hate this example. Okay? Good. Now, okay. Now we're going to learn actually what's the Gibbs energy. So we run 3 laws of thermodynamics now. First law of thermodynamics, second law, and then today we learn third law of thermodynamics. So third law of thermodynamics is for any kind of stoichiometric crystalline phase, the entropy of those crystalline phase, solid crystalline stoichiometric phase at 0 degree Kelvin is 0. Okay, that's third law of thermodynamics. Okay, and now let's learn Gibbs energy. So finally. So Gibbs energy typically notated as G, and then Helmholtz energy, there's many ways, but typically we say A. Okay? And some people using actually Helmholtz energy as F. So it's depending on actually the textbook, or depending on the authors, people using different actual notation. But at this Gibbs energy, typically we say G, capital G. Okay? And in the past, actually, people say that, okay, Gibbs energy and Helmholtz energy, this is free energy. Free energy. Okay? So, if you look at actually all the textbook, they always say that Gibbs free energy of the system. Okay? Or Helmholtz free energy of the system. But now, I mean, in this day, we just remove this free. I mean, everyone knows that, so there's no reason to still say the free energy. So Gibbs energy and Helmholtz energy is kind of the potential energy of the system, inside of system. We can just assume in this way. So total amount of energy of the system, we call it kind of the internal energy, and the Gibbs energy is kind of potential energy to do some kind of work or chemical reaction. That's actually, we call it free energy, and then that's actually Gibbs energy. It's very difficult to really distinguish these two, but let's put it in this way. Okay? So whenever we actually learn the material engineering, we're actually using the Gibbs energy. And in the physics, people still using a lot of this Helmholtz energy. And also, when you go to the mechanical engineering, they prefer Helmholtz energy. Because by the definition of Helmholtz energy and also the derivation of Helmholtz energy for the certain equilibrium criteria, Helmholtz is much more applicable. Helmholtz energy is more applicable for the mechanical engineering example. But in the material engineering example, Gibbs energy derivation of Gibbs energy is much easier to apply to understand chemical reaction, especially. Okay, that's why we prefer to use the Gibbs energy instead of the Helmholtz energy. But anyway, so let's look at how this one defined and what's the actual really significance inside of this concept. Okay, so let's take one Helmholtz energy. Let's take this one first. So Helmholtz is, in fact, named after a scientist called Helmholtz. Okay? When Gibbs actually first introduced when Gibbs first published his paper, nobody wanted to accept the Gibbs energy, the concept of Gibbs energy. Okay? Gibbs was born around actually Boston in USA, and when he actually become about 20, 30 years old age, Helmholtz was already very big scientist in Germany. The German and all this Europe, they actually start to actually develop the engine, steam engine and etc. So Helmholtz was one of the godfather kinds of the engine design, the conceptual design of the engine. And then nobody understands what Gibbs was talking about. And luckily, that paper somehow get into the Helmholtz actually desk of the Helmholtz, and Helmholtz actually see some impact of the concept. So that's why Helmholtz really appreciate the work of the Gibbs. That's why Gibbs was very famous in the end. But otherwise, probably Gibbs will just die without any pain. Okay. And unfortunately, Gibbs energy is so much used. But however, Gibbs was not very famous during when he was still alive to work, during in the 1920. So he was not his work was not very much appreciated by the many people. So he could not get the Nobel Prize. And however, the successor got a couple of the Nobel Prize in the end. But unfortunately not for him. It's too bad. And it's in terms of in the physics, if you say Einstein, in thermodynamics, it gives, that kind of level. But unfortunately, he could not get any Nobel Prize. Okay. But anyway, so Helmholtz energy. So why we actually introducing this Gibbs energy, Gibbs free energy, or Helmholtz free energy, or Gibbs energy and Helmholtz energy is, we want to know whether my system, we want to actually find a certain criteria to define my system is equilibrium state or not by using only system related value, not surrounding. Okay? When I have something inside of happening in the system, I want to make a function of those things by using certain I want to make a certain function, but I want to use that function to dictate whether this system is in equilibrium state or is it still going for the spontaneous reaction. Okay? And first law of second law of thermodynamics was very nice. However, it have to count system as well as surrounding to know whether my system is equilibrium state or not. Okay, that's why it's not practical. And so people was thinking, and then Helmholtz and Gibbs actually really introduced new function which can really use to dictate spontaneous reaction or equilibrium of the system by using only system value. Okay? That's why it's very, very important. Okay, let's look at how they actually really derive, how does actually really those concepts is really working. So Helmholtz energy start from the internal energy, U. Yeah. So let's take, for example, reversible process. Okay? So it means du of the system. Now we're actually really introducing system. du of a system equal to dq. Because it's reversible, so it's reversible minus dw reversible, yeah? And dq. So ds was defined as dq over the t. Okay? dq reversible is same as ds over the system. Am I right? So total amount of heat I need in the system is the system energy, system entropy. Okay? If it is irreversible process, it's not like this, but this for the reversible process, this work. Okay? So then this will be dq of reversible can be changed as so t ds of system minus dw reversible. And then let's move this one here. So du of system minus t ds of system equal to minus dw reversible. So this is minus, if you just only considering the PV work, so this is P dV. Is it okay? And then here, Helmholtz actually introduced his energy. So Helmholtz said that, okay, how about let's define A equal to U minus TS. Okay? Then if I make a derivative, dA equal to du minus tds minus sdt. And then let's take assumption, say that constant temperature. Then this becomes 0, yeah? So then this will be dA equal to du minus tds. So dA of system, du of system, tds of system. Okay? So we assume this one first, constant temperature. Okay? So then this will be dA equal to, I'm going to make it 0 when constant V. So we have two assumptions, two constraints. At the constant temperature and the constant volume, dA of system becomes 0 for the reversible process. Okay? So reversible process is equilibrium state. Equilibrium state. So this is equilibrium state basically. At constant T and V, actually that's the constraint. But whatever it is, at least we found now, okay, if I actually defined my A equal to U minus Ts, internal energy minus Ts, and then if I assume this is constant temperature condition, constant volume condition, and if it is equilibrium state, dA should be 0. dA of system should be 0. I don't care about the universe at all now, only system. I can only dictate something happening inside the system by using the function A, and I can say that whether this is equilibrium state or not equilibrium state. Okay? That's beauty of this equation. Okay? Now, okay, so that's a reversible process. How about then spontaneous reaction, irreversible process? Okay? So let's look at now irreversible process. Okay, so now 2. So we are doing same thing, du of system equal to dq minus dw. Is it okay? So now ds of system equal to always same as dq of reversible over the t. Whether it's reversible process or irreversible process, I don't care. System entropy is always defined by reversible Q. Because if this is irreversible process, the heat will be generated by the regeneration, or heat will be generated from the work, yeah. Part of work will actually generate heat, and that actually compensate the difference of irreversible heat, and then this is actually the reversible heat. That amount will be generated from the work automatically. So the system entropy, when you talk about system entropy, is always defined in this way. Okay? So if you look at now, I mean, from this irreversible process, so this means this will be T of dQ plus So this is same as this quantity, yeah? So this can be cancelled out in this way. Okay? So if I take only this one, dq irreversible, then T ds of system minus dq reversible minus dq irreversible. Is it okay? If I leave this one and then if I move everything on the other side, and then if I actually multiply temperature in both sides, then TdS equal to dq irreversible, TdS minus dq reversible minus dq irreversible will be dq irreversible. So I'm replacing this one. System minus is it okay? So I'm moving this one again. Or dV, whether reversible work or irreversible work, anyway, it's pdV. Okay? And now, constant temperature and the V condition, so we can replace this one again as dA of system. So this is exactly the same as dA of system here, yeah? Equal to, this is 0, so minus this value here is positive all the time, yeah? Q reversible is always higher than Q irreversible. So this is always positive. So it means this become negative value. And this is for irreversible process or natural process. Okay, that's interesting, yeah? So now I want to actually see whether my chemical reaction or something happening inside of my system. I want to really say, okay, whether this one going to that direction or this direction. Okay, that's a natural process. It's moving. I'm still moving to that direction or this direction. Is it going to move this way or that way? In order to actually dictate that, if I make my system as a constant temperature and constant volume, then by using the Helmholtz energy, if Helmholtz energy is decreasing, if that direction is make Helmholtz energy become decrease, then it means it's a spontaneous reaction. It's happening in that direction. Okay? And then when you move and move and move, at a certain point, dA becomes 0, then it means I am reached to the final equilibrium state. Okay? It's nice, yeah? Now finally we got the one function which can tell spontaneous or equilibrium condition in the my system by using only system value. That's important. I don't have to worry about surrounding anymore. Is it okay? Good? So, using the similar concept, Gibbs actually derived another one. So this actually one of the problem is constant temperature and constant volume. But in the material engineering, typically we need constant temperature and constant pressure. So CP, I told you, CP is more important in the material engineering because most of the time we don't care about pressure. Okay, so it's constant. So Gibbs actually tried to actually develop another function which can be applied at constant temperature and the constant pressure. Okay, so that's actually Gibbs energy function. So 2. So Gibbs start with enthalpy. Okay, so let's take this way. So enthalpy of system. You good? Then let's make a derivative. dH okay, du equal to dq dw, and dw is same as pdv. Okay, sorry, not in this way. Same as this one. So this will be vdp directly here. Okay? So, I mean, reversible process is so easy. Let's take irreversible process directly. So, dq, irreversible process, will be same as those value here. ds, system, minus correct? So we are taking this one inside here when it is reversible or irreversible process. When it's reversible process, this is same as reversible, so it becomes 0. When it's irreversible, there's certain difference. Okay? So dq, so dh system, and then one dq of system. I'm moving that one, t ds of system equal to dq part, the less of the part, minus dq reversible minus dq irreversible plus v dp. Okay? Now we are making definition of Gibbs energy. G equal to h minus ts. So this is the reason why you actually define in this way, to replace this one as Gibbs energy. So dg dh minus tds minus sdt. Constant t, this is 0, so dg system equal to dh system minus t ds of system. Okay? And now I'm replacing this one here. So then this will be dg of system, Gibbs energy of system, derivative equal to minus dq reversible and then I want to also make assumption, constant pressure assumption here. So this is constant temperature assumption, constant pressure assumption. Then this will be like this. So this means dg of system equal to 0 when it is reversible process. Because reversible, when it's reversible, irreversible one, reversible one is same. So this becomes 0, yeah? Or when it's irreversible process, this become positive and so it become negative again. So this is 0 or less than 0. When it's 0, so equilibrium state. When the system is equilibrium state, the Gibbs energy change in the system, whatever direction it is, becomes 0. Then that's equilibrium state. When the Gibbs energy is still decreasing, that's a spontaneous reaction. Okay? So dg of system is always decreasing or become 0. That's the natural process. And then equilibrium state at 0. And dA of system is same thing. It's decreasing or 0. But two of these two equations cannot be applied in the same condition. One is constant temperature and pressure, then dG. And the other one, constant temperature and volume. When you say in that condition, you have to use the dA. That's the two difference. But as I mentioned in the material engineering, we used more dG, Gibbs energy, because most of the time we have constant temperature. At least temperature should be same. Otherwise, I mean, temperature is different. Two material is different temperature. Then it's not equilibrium state. It should be at least same temperature. So it's natural, same temperature. Otherwise, there's still something moving from the one to the other one. Yeah? Should be same temperature. And then when the system, and then if the system is constant pressure condition or constant volume condition. But in the material engineering, we typically don't care about the pressure. It means it's constant pressure condition. Okay, so that's why we use more Gibbs energy than we frequently use Gibbs energy than the actual Helmholtz energy. Okay? Good? So finally, we derived the Gibbs energy. So now we're going to do the main game of the thermodynamics. Okay? From next week, we're going to really now use the Gibbs energy and then do the some Gibbs energy, energy calculation. Any question? No? Good. Then see you next week.